Hi, welcome to my project presentation. My name is Iddo, and the project was made for my Introduction to Algorithmic Development in Java course. During this presentation, I'll show you some aspects of my project. Let's get started. For this project, we had to write a puzzle solver for any given puzzle. In our example, it was a three-dimensional maze. To solve such an abstract problem, we use generic classes and interfaces which define certain functionalities, such as a solver interface, which had one function, solve, or a solvable interface, which defined several functions. To implement these interfaces, we used generic algorithms such as BFS or A*. How do these algorithms work? Both these algorithms maintain two lists, an open list and a closed list. The open list keeps the states we haven't seen, while the closed list keeps the visited states. Each state has a cost, which is calculated by how many steps it took to get there. By ordering these states by their cost and evaluating first the lower cost states, we promise the cheapest solution available. Let me show you how my program works. First, you're going to have to start the server, which will handle the client requests. Command line interface, so you're going to have to write start for it to start. Now, let's start a couple of clients. That's one, and that's another. Now, I'm going to show you what the solve button does. So we're going to want to generate a maze. Just give it some values. And once we click solve, we're going to see that the server will actually handle the client. Let's try both of them at the same time. Same size mazes. And once I click solve, you're going to see that the server is handling the client. I will show you that right now. As you can tell, the server handled both clients pretty efficiently. The solutions that the server solves are then saved and compressed, so that the next time, if we're going to want to see the solution, or if we're going to want to solve the exact same maze, you're not going to have to ask the server to solve it again, but you're going to just have it cached in the map. So you have a gzip output stream, which saves the solution in a compressed format. Now the solution shows pretty nicely on the client side, and I'm going to show you that just now. This one is still running, so I'll just use this one. New maze, 15, 15, 15. Wait, the other one just finished. And once we click solve, it'll just go throughout the maze and solve it automatically. It's gonna take some time because I made a pretty big maze, but other than that, it works well. It works. It also pops up a small U1 window, which is nice. So let's say it finished, and we want to exit. So now we're back in the server, and we click on exit. The server was waiting for all its processes to shut down, and once it does, it's going to shut down itself. In this project, the client side uses the MVP, or Model View Presenter design pattern, in which the model is the brains of the application, the presenter is the router of each request, and the view is the user interaction. In this design, the presenter is an observer, and the view and model are observables. That means that they do not even know about the presenter, which leads to better code separation between the different parts of the code. So here you can see that the presenter is actually an observer, that the model is in fact observable, which means that the presenter can register to view all of its notifications. Our view can be either command line interface, CLI, or a graphical user interface, GUI. Our GUI, and I'll demonstrate right here, uses different kinds of widgets, which create its look, such as the menu bar or different buttons. Each widget is then given a different listener, which tells it what to do when the widget is interacted with. The listeners usually notifies the observers what happened. Then the presenter will take the update and analyze it to decide what to do with it. So as you can see here, the update function checks which part updated it and then decides what to do with it accordingly. In our project, we use the command design pattern, which means that the events from the view are translated into commands, which are different classes in our project that interact with the model and run certain functions there, such as a generate command or a solve command. These commands are run as separate threads within a thread pool in our model so that our client won't crash from too many requests. So right here we have our different threads, different functions in our model, and we have a thread pool which executes each command, as you can see here. In my project, the solve command is then transferred to the server over a network socket. Then the server solves the requested maze and replies with a solution, which is then cached in a compressed form. So in the solve command, you can see that the network socket is being opened, and then it tells the server that it wants a solution. It sends it the maze, and then the maze gives it back the solution object, which is cached in the solution map. And when you exit the program, it is saved in a file in a compressed form. The solving algorithm we used in this project, we can see right here. Like we said earlier, it has an open list and a closed list. You take the first state from the open list, which is the cheapest one, and then you iterate over all of its successors and set the cost of each one and put them in the correct list. You do that until you can find the wanted state, the goal state, from which you start backtracing and making the solution, which is then returned once you've reached the final state.